You don't have to settle for a job that makes you unhappy, and you don't have to go through the pain of searching through millions of job listings. Hired.com brings job offers to you, the engineer. Hired is a job marketplace built for the engineers. A few years ago, I was unhappy with my engineering job. I felt stuck, I felt underpaid, I felt alone, and I didn't know my value in the job marketplace. It's a very opaque market. So I used Hired.com to find a new position. Hired connected me with a talent advocate who guided me through the process, like a free concierge. They made me feel valued. It was like a white glove service. And this talent advocate helped me with all the questions I had. Should I ask for more money? Should I consider relocating to try to get a higher salary or a better job? The talent advocate that you get paired with on Hired.com helps you with all these kinds of questions. I got several job offers, and I found one that was a good fit. In fact, engineers who use Hired.com get an average of 5 offers from great companies like Facebook, Uber, and Stripe, and the companies are bidding on you to try to get the best engineers, and so you end up with the higher salary. Go to Hired.com/SEDaily for a $4,000 bonus upon signing up. It is completely free to engineers looking for a job. I've interviewed the founder of Hired, Matt Mitchkovich. He also started 99 Designs and SitePoint. He's a software engineer, and he understands that engineers deserve the leverage in this super competitive market where great engineers are at a premium. Check out Hired.com/SEDaily. I'm happy to advocate Hired to my listeners because it puts power in the hands of engineers. Now let's get on with this show. Holden Karau is a principal engineer at IBM working on Apache Spark. Holden, welcome to Software Engineering Daily.
Thanks for having me.
Spark is a product that many of the listeners are interested in, and many people have a light understanding of what Spark brings to the table. So let's start a bit by talking about how it works at a high level. What is Apache Spark?
So Apache Spark is a really fast general purpose engine for doing large-scale data processing. So if you're coming from sort of a MapReduce world, it can replace a lot of the sort of traditional MapReduce applications. One of the standard benchmarks shows it like it's substantially faster than Hadoop MapReduce. But honestly, I came to it mostly not because of its speed, but because I really like its very clean API. And it has a sort of very functional style API, which I find really intuitive. And it has like a bunch of different libraries for the different components. And unlike sort of the traditional MapReduce systems and other parts of the Hadoop ecosystem, these things all ship together. So we get Spark SQL, we get machine learning, we get graph libraries, and this all comes in sort of a single package. And so you don't have to install a bunch of different things and figure out how to get your data from one system to the other. They all just work together really nicely.
Yes. Okay. So we certainly have the API, which we'll get into. There's also the abstraction known as the Resilient Distributed Data Set, or the RDD. What is an RDD, and why is this important to Spark?
Yeah. So RDDs are Spark's sort of core abstraction for dealing with distributed data. And they're really cool in that they don't actually exist in sort of the way that we would normally think of a distributed collection. What happens is sort of we'll use the Spark context to load some data into an RDD, but it won't actually do any of the work until we go ahead and do something called an action. So we'll load some data, we'll write a bunch of computation on it, and as we write this computation, it'll just keep giving us back these new RDDs, and these RDDs will keep this information about sort of what is needed to compute the data inside of them. And once we perform an action, Spark is able to look at this lineage graph and compress a lot of things down so that we don't have to do like as many passes over our data. And, we can, if we're unioning from multiple sources, it can figure all of this stuff out. And it lets programmers be really, really lazy. And it does this through this thing called lazy evaluation. And it can also be a little bit confusing sometimes because you can load data which doesn't exist, and you'll only find out much later on in your program when you, say, go to save it or perform a count, which requires evaluating the data inside the RDD. So it's really powerful and a little bit confusing at the start, but I think it's a pretty powerful concept, and once people pick it up.
Absolutely. You mentioned the lazy evaluation aspect of the RDD, but there's also the aspect that it provides fault tolerance. So how does an RDD achieve fault tolerance?
So RDDs achieve fault tolerance in sort of a very different way than traditional MapReduce does. And it does it through this lineage graph that it's constructed in the lazy evaluation. And so what happens is if we lose some of the information, right, like a node disappears while we're computing our data, Spark looks at the lineage graph to figure out what sort of things it needs to do to recompute that data, and it simply goes ahead and recomputes the missing bit of data for us. And the traditional sort of MapReduce approach is to write it out to a bunch of different machines and store it on disk on a bunch of different machines and achieve resilience that way. But writing out to a bunch of disks is kind of slow, and recomputing a slice of your data can be much faster. And for things where you do actually want to write it out to a bunch of disks because your compute is particularly expensive, you can do that explicitly in Spark through checkpointing.
But so this idea of having a fault tolerant mechanism through lineage, so does this mean that we have to save any additional data, or give me a more in-depth kind of construction of how a lineage works?
Sure. So, I'm going to come back to the word count example because it is pretty much...
It's canonical.
It's the canonical, simple example, and we've seen it in pretty much all of the other systems. So what you'd do is you'd start by reading in a text file, then you'd do a flat map, and you'd probably do a map and a reduce by key. And then we would probably save the results out or something so that we actually trigger the evaluation. But let's say during that, right, we lost one of the nodes, right? Spark will go to its lineage graph, and the lineage graph was actually constructed while we were doing the flat map, and reduce by key, right? We didn't have to be explicit about these are the steps to take to recompute. Through the operations we've done on the RDD, Spark has simply built up this graph for us, and so we don't have to worry about it as sort of application developers.
Okay, I understand. So this idea of lineages, I don't know how much you've looked into it or how deeply you understand it, but there's an upcoming interview that I'm doing about Tachyon, and I'm curious if you have any understanding of how the idea of lineages translates to the storage layer, which is kind of the problem that Tachyon is handling.
Sure. So I don't actually really use Tachyon all that much. Just the systems that I work with tend to not really need it. So I probably shouldn't talk too much about it. But I can talk about how lineage and caching interact in sort of a more general way. That'd be perfect. Cool. So let's say we constructed this word count, and then the word count involves a shuffle, so that's kind of an expensive operation. So we cache it, right? So that, just in case we need to look at the word count again, maybe we're going to look at the top 10 words later on, we don't have to recompute the entire data. But it's possible that one of the nodes will disappear. So when we cache, by default, it's just going to cache in memory on one of the nodes. And if that node disappears, when we go to reuse that RDD, Spark still has the lineage information, and it'll use that lineage information to recompute that missing piece of data. Now, since we had a reduce by key, and that's actually a shuffle step, there's these things called narrow and wide transformations. And narrow transformations are things where we know exactly which partitions in the previous RDDs were used to compute my new partition of information. So things like map are really clear because it's just this one-to-one, my inputs were X, my outputs are Y. And so if we lose part of X, we know we just need to recompute this one little bit. If we lose part of y, we know we just need to recompute this one little bit. But since we had a shuffle, we actually have to recompute a lot of things. But that's okay, right? But so we'll do the recompute, and we'll get the value, and it'll use the lineage graph at that point. But if we had like some really expensive wide transformations, it might actually be worth it to cache it to multiple machines, right? In the word count example, it's probably overkill, but when we're caching, we can also tell Spark, like, this is some really expensive information to compute. I'd like you to cache it to 2 machines to decrease my chances of a problem if one machine disappears, right? It's not like a problem in the sense like it's something our code has to handle. Spark handles it for us, but it'll give us like better sort of performance characteristics in case we lose some of the machines in our cluster during our job.
Okay, great. So we've dove down pretty deep at the beginning, and so I want to kind of zoom back out to something you said. You described Spark as a general purpose distributed system with a really nice API, and the API of MapReduce, Hadoop MapReduce, is simply map and reduce. How does that contrast with the API of Spark?
So Spark has, and I'm obviously going to be pretty biased, but it has a much richer API, right? Like on RDDs, we can do maps, we can do flat maps, we can do arbitrary reduces, we can do reduce by key. When we're writing our code, right, one of the things which I think really lends itself to having a much cleaner API is that Spark is able to sort of put all of these sort of maps together into a single stage, unless there's like wide transformations. And one of the things which I see sometimes making sort of MapReduce jobs complicated is like doing an individual like map is really computationally expensive, and so people will put a whole bunch of different logic inside of the same map, and they'll use a bunch of tricks to like output to different files. And in Spark, we don't have to do that, right? We can just write our code in like a much more natural way, right? We're not sticking 3 RDDs together to try and produce a union so that we only map over our data. It's taken care of it for us.
These hacks upon hacks that we have to do for Hadoop. So is this because basically because Hadoop MapReduce has to write to a stable storage format so often, and we're lumping in these hacks to try to cut down on the disk writes?
I think that's a lot of the hacks that you see in the Hadoop space, is that the cost of doing a map task is very expensive, because at the end of it, you have to write out to a bunch of disks, and that's really slow.
So how does this contrast with how frequently Spark has to write to stable storage?
So Spark doesn't have to write to like stable storage like HDFS ever, unless we actually want to persist our data there and use it in a future Spark job or pick it up for analysis in some other program. It sometimes writes to local disk and disk on other workers, but it doesn't have to use HDFS. There are times when checkpointing to stable storage can be really important. And one of the cases where this sort of shows up sometimes is in the graph libraries and sometimes in streaming as well. And essentially, our lineage graphs can get pretty complex. And for the most part, when we're just writing sort of natural transformations as a programmer, our lineage graphs don't ever get so complex that they're not reasonable to sort of keep around. But if it gets to the point where like our lineage graph is out of hand, we can checkpoint it. And then what Spark will do is it will use sort of the MapReduce style of being able to recompute by reading from disk, as opposed to doing a raw recompute. So we're not particularly forced to, except in streaming in some cases, and in some of the graph libraries they do checkpoint, because the lineage graph can get very complicated with all of these iterations on the graph.
Okay, I understand. So as you mentioned before, Spark brings a number of different distributed computing tools that, in the Hadoop world, maybe they would be split out into all these different products, and it brings it into a single project, which is Spark. So what are the types of tools that Spark is unifying together?
So Spark has done a really excellent job of unifying SQL and machine learning, as well as graph libraries. I think the SQL and machine learning are really exciting because they're starting to be built together. You see Spark's new machine learning pipelines are actually built using DataFrames, which are a concept from Spark SQL. So it's able to take advantage of some of Spark SQL's optimizations beyond the optimizations that were made in core to support Spark SQL. And then streaming is also really interesting, and you can see that growing together with Spark SQL as well. And a lot of the work that was done to make sort of streaming feasible benefits all of the projects. So, for example, streaming depends on really, really low task overhead, because if it's really expensive to make your tasks, right, like microbatching isn't going to be a reasonable strategy. So there was a lot of work done to sort of lower the task creation overhead, and that benefited all of the projects that are built on top of Spark, not just Spark streaming, right? So by building all these things together, there's a lot of work done to improve this common core that all of the projects are able to benefit from.
Okay. So one of the things you mentioned is Spark DataFrames, which were introduced last year. What is a Spark DataFrame?
So DataFrames are really cool. But if there's people listening who are coming from sort of maybe a Python Pandas background or an R background, before we go too far, it's important to keep your expectations in check, because these are sort of distributed systems, and the API that's available isn't necessarily quite as featureful as you see in Pandas or things like that. So sorry to your Python listeners. The data frames are not quite magic. But with that wonderful disclaimer sort of to its side, data frames are this programmatic way of making Spark SQL accessible so that we can write just normal Scala, Java, Python code, and not be constructing SQL queries to get access to data frames. And so they have many data frame-like properties, right? Like they have a schema, they have this sort of restricted set of types that they support, and they build up sort of more of a logical plan than that Spark SQL is able to do a lot of really cool optimizations on. And on the optimization standpoint, one of the tricky things for Spark with RDDs is group by key is actually really, really unsafe on an RDD. If you call group by key, Spark will group your data together by key, but that could make your computation fail because it'll try and put all of the records together. And you might have done a group by key followed by a reduction, but Spark can't really introspect your reduction and figure out what's going on. But inside of data frames, the API doesn't allow for pure arbitrary Scala code. So when we do a group by key and then we do a reduction, Spark is able to look inside and see, oh, this is the kind of reduce you're doing, or this is the kind of aggregation you're doing. Let me go ahead and I'll pipeline these together and I'll actually do things intelligently.
Right.
And so data frames are really exciting because I'm really lazy and they take care of this whole class of optimizations for me. And I can just let the Spark SQL optimizer worry about it.
Okay. That's very interesting. So, to maybe put a capstone on that, would you say that data frames organize our data into named columns, kind of like a database table?
Yeah, they're very similar with named columns. They can be sort of nested. So we can have more complex structures than perhaps we're used to in sort of maybe a more traditional database, but we can think of it similarly. Okay.
And how does Spark usage, you've been in the Spark community for a while, so how does Spark usage with data frames compare to working without data frames?
So, working with data frames, your code can be a lot faster without as much work, but there's still this, it's a newer component, as you pointed out. And there's cases where it just doesn't work yet. And these can be kind of saddening because you want to use the new shiny thing, which takes care of everything for you. But sometimes taking care of everything for you doesn't quite work. And then you need to bring it back to an RDD. But thankfully, it's really easy to bring back to an RDD. And so like working with DataFrames is a little bit of a different model of thinking about it. You're thinking about more sort of relational type transformations as opposed to functional type transformations. And sometimes the Spark SQL optimizer doesn't get everything quite exactly correct. And then we need to like use an RDD. One thing that I'm really excited about in Spark 1.6 is the datasets API. And they allow us to do sort of functional transformations on strongly typed datasets, which are still in the Spark SQL optimizer, but allow me to write code which is more sort of how I think. So I tend to think in a more functional way than a relational way. And that's just me personally as a developer. So I really like datasets because they match my mental model of the world a bit better. But like different people can have very different, personal choices.
Certainly. Engineers are always looking to simplify. To simplify testing and deployment, engineers turn to CodeShip. CodeShip is continuous integration and delivery as a service. With CodeShip, your tests are executed against your code automatically whenever you push to GitHub or Bitbucket. On Software Engineering Daily, we've done several shows about DevOps, and continuous deployment is key to DevOps. It's a great way to break down the wall of confusion between development and operations. Managing your own testing infrastructure is painful. That's why you want a service like CodeShip to do it for you. If you have a huge number of tests, you can use CodeShip's Parallel CI to run all your tests in parallel. CodeShip will spin up containers on their own infrastructure to run your tests in parallel. If the code passes your tests, CodeShip will deploy it automatically to your users. Companies like Product Hunt are already using CodeShip to speed up and simplify development. To sign up for free and start shipping today, go to codeship.com. Or to try out CodeShip's new Docker platform, go to codeship.com/Docker. So how do DataFrames make it easier to program machine learning jobs?
So this is really exciting, at least to me, because I'm a nerd. But DataFrames make it, so there's the pipeline model in Spark makes it a lot easier to put together a lot of sort of data cleaning and data preparation type things and sort of keep them together and work on these data frames. So I can take a data frame and I can feed it to this pipeline. And the pipeline will have like, maybe it'll take my strings, it'll turn them into indexes. I might have another thing that's normalizing some stuff and like all of my standard sort of data cleaning things. And at the very end, it'll output a model. But my model can have all of this data cleaning stuff inside of it for when I'm bringing in new data to predict, right? I don't have like this separate pile of code to like clean my data and then this machine learning library that's over here that only works on like clean data. They sort of come together and they work on data frames. And they use the schema information inside of data frames in really powerful ways. So like your machine learning stuff needs to, know certain properties about, the data that it's working on. And it attaches some metadata to these columns as it's sort of processing this data and getting it ready for the machine learning library. So I think it's really cool.
Right. Anyway, the conversation around data frames is a good segue to talking about Pandas, and you already touched on this. Pandas is a data analysis library in Python. And the Python users of Spark are increasing. I saw a talk by Matei where he showed this graph of like how fast Python usage is increasing. It's pretty interesting. Describe how Pandas interfaces with Spark.
So that's a really good question. And I might take a few tangents along the way, if that's okay.
Go for it.
So I think Spark and Python are a really great match, especially for for data scientist people. And one of the downsides of sort of PySpark is there's this overhead in getting data from the JVM to Python and back. And DataFrames are really cool because they don't have this problem unless we're writing complex UDFs. But essentially, we're able to express our transformations in Python on the data frame, and the computation is able to be done inside the JVM because it's using sort of this consistent API between the Scala and Python things, and it's not having to sort of use arbitrary Python code. So I think that's really exciting, and there's some huge performance speed up for PySpark users. If your stuff can be done in a data frame instead of on an RDD, there's a really good chance you want to be using data frames. Like, even if it's a little painful as a developer, the speed up is well worth it, in my opinion. And so the next question, or getting back to the actual original question, is how Pandas and Spark work together. And this is something that I care about. One of the things that I've worked on with Juliet is something called Sparkling Pandas, which is a project to provide a Pandas-like interface on top of Spark's data frames. And this is just, accepting that most people already know the Pandas API. It would be really good if we didn't have to teach them another API and they didn't have to rewrite their code. That being said, Sparkling Pandas, we haven't had enough time to work on it lately, so it's an interesting proof of concept, but it's not something that people should be using today in production. I'm focusing most of my time on Spark. I mean, Sparkling Pandas, the real goal of it, in this ideal world with like happy pandas and lots of bamboo, is that we'll make it so that people can take their pandas code, that they can just do the data analysis that they've been doing on small data, and they can start to do it on larger scale data without having to really change their mental model too much, right? Mm-hmm. Like, they might find some things are missing, and they'll have to work around that, but they won't have to like completely relearn everything. Mm-hmm. And that's like a goal. It's not a goal that we've reached, unfortunately. Right. So it's actually, there's a lot of different techniques that we do to sort of kind of make this work. And some of the things that I talked about sort of briefly was like that writing Python UDFs is kind of slow. So, you shouldn't do that. And so what we've done is we've taken some of the things which, are done in Pandas, which you would traditionally have to do, as a UDF on top of Spark data frames to provide support for. And we've written Scala UDFs for them and done some really terrible things behind the scenes to make them work. Namely about, we, in our code, lie that we're inside org Apache Spark to touch internals. But, we do things sort of in more of a practically focused way of like, this is what the user wants to do. How can we enable it, even if it's a bit expensive? And sort of the Spark data frames thing is more focused on like, these are the things that we can do in distributed systems really well. Let's make a really nice, simple API for that.
So, sorry, for listeners who don't know the acronym, what is a UDF?
Oh, right. Sorry, I completely spaced on that. So a UDF is a user-defined function. Okay. And essentially, we can think of it as like adding sort of some backdoor extensions to Spark SQL. So like it doesn't have kurtosis, so we added kurtosis. And we do things like earlier versions didn't have certain statistical aggregates that we were interested in. So those are also sometimes called UDAFs, for user-defined aggregate functions. But
okay,
yeah.
Well, so Pandas and Spark both have data frames, but the eagerness of the data frame evaluation is different. Could you describe this difference in more detail?
Sure. So on a Pandas data frame, when I do an operation, it's evaluated immediately. And this is cool because I can see if I've made a mistake, which is really quite useful. But it's a little unfortunate in distributed systems because sometimes, evaluating a single operation is kind of expensive, and it would be much better to look at the set of operations you were interested in doing and sort of figure out, if there's any way to put some of those aggregates together, right? Like maybe while we're computing the average, we can also compute the standard deviation. Let's do those things at the same time in a single pass over the data. And so, they sort of come from these different backgrounds because of the types of systems they need to run on. But Spark SQL's DataFrames aren't like 100% lazy. So if we try and load data that doesn't exist with JSON, for example, right, it'll try and do some schema inference on it, and it'll say, oh, hey, this data doesn't exist, right? But if we were doing this in just regular Spark, and we tried to load the data, it would go like, hey, it's okay. And it would only explode later on once we asked it to save the results.
Sure.
And so DataFrames are sort of like in between sort of traditional eager evaluation and Spark's like more fully lazy evaluation in RDDs. And so they sit in this sort of middle ground where some of the information, namely the schema, is sort of more eagerly evaluated.
So you're going to be giving a talk at Strata plus Hadoop called Testing and Validating Spark Programs. What will you be trying to convey in that talk?
Yeah, so I come from perhaps more of a industry background than a lot of the other Spark developers who come from more of an academic background. And so my focus is maybe a little different sometimes. And one of the things that I feel is really important, and we haven't necessarily done a lot of work around enabling, is making it easy for people to write tests. Because software without tests is just asking to be woken up at 2:00 in the morning. And I like to be asleep. And validation is this other thing, which is also really important to me. And it's not so much about being woken up at 2:00 in the morning, although it can stop that sometimes. It's more about, keeping my company from losing all of its money so I can still get paid tomorrow. And sort of where this comes in is a lot of these big data jobs are being used to drive really, really important things. And data sources, like, even if our code is perfect, right? Like we're not making any mistakes. And I mean, if you're doing that, please come and interview. But, if you're like me, there might be some mistakes in your code. And even if there isn't, our upstream data sources sometimes change without necessarily communicating to us that they've changed. And the results we can produce can quickly become garbage. And in my opinion, it's really important to try and have some tooling around catching this before we use the models or reports or whatever the product of our software is for actual serving our customers or decision making, because using incorrect information could be disastrous. Like if we were maybe trading based on historical models we've been trading, I think we've seen that explode a few times.
Oh, yeah.
I personally have done some really terrible things with recommendation software that I regret. And, I was younger and I learned the very hard way that I should have more sort of validation around my jobs. And so these are things that I'm really passionate about. And I think a lot of software developers, everyone knows we should be writing more tests. Maybe not everyone knows we should be validating our output, but if you say it to most people, they're like, oh, yeah, that's a thing. That's important. And if you're at a big enough company, you probably already have internal tooling around this. But a lot of these things are internal to each company, and I think it would be much better if we had sort of some more standard sort of tools around this. So I'm going to be talking about some of the tools I've built for testing and validation, as well as some of the other tools for testing.
So this problem seems so intractable to me, because it's like you've got your machine learning algorithm or whatever your Spark program is, and it's running on some big data set. And a lot of the potential problems you can have seem like they emerge from the changing nature of the data set. And And a lot of times, the way, at least that I understand, that a lot of these systems are tested is you make some kind of dummy data set or sample data set, and you're running your Spark application on this example dummy data set. So whenever your application changes, you run it against the dummy data set, but that doesn't really say anything about how you're testing the I guess the reliable or the unchanged schema or the basically the integrity of the underlying data. But I guess my rant in question format would be more like, how do you create a system that averts those types of data integrity problems?
Right. So that's more focused on the validation side.
Okay.
Really have a good idea of how to do that in sort of compile time or like inside of unit tests or even standard integration tests, right? Like there are some things you can do, right? Like data sets are typed and we can check the schemas of our input data. But I think a lot of times what's happened is like, and normally if the schema's like changed, like the explicit schema's changed, like our software will fail, and that's fine. Like,
you want to fail.
It didn't run. That's great.
At least it didn't trade away the company.
Right. Yeah. I still have a job tomorrow. A stressful job, but a job. And that's like one of my key tenets is like always remain employed. Except, being on a green card. Sorry, H-1B. It's very important. But sorry. Right. So back to the validation side. So the validation side would do things like, the places where I've seen things happen is like one of my data sources just like simply it went away, but it went away in such a way that they just started returning like no records. Or like I've seen things where I only get a fraction of my data. I see things where like sometimes one of the fields that I depend on has changed meaning. So the sort of model that I'm producing really doesn't make any sense anymore. Like I was assigning a lot of weight to this thing, and this just doesn't make any sense. And the ways to catch that are sort of multi-step. So catching like missing data is much simpler, right? Because Spark has these internal counters about sort of like, how much data did I read? How much data did I write? And so one of the things that you can really easily do is say like the number of records that I read today should be roughly equal to the number of records that I read yesterday. Or if maybe you're Pinterest, right, like it should be 10 times the number of records I read yesterday. You can like define a relationship based on sort of your historical things. And you can say like, today should be about similar to what last year was if you were in retail or something like that, right? And another one is there's these things called Spark accumulators, and there's very much of a side tangent about how Spark accumulators are not necessarily the best system because they have sort of this double counting problem. But one of the things we can do in sort of like validating our models is we can keep track of like the number of people that we've produced recommendations for versus the number of people we have no recommendations for. And we can sort of keep track of like, the number of queries that, from our test set don't produce results anymore, or the percentage of queries that have like substantially changed. And we can use this to say, it's not, sometimes we're going to get like a false positive that says like, hey, stop the build. But I think that's okay if we sometimes get a false positive and then go investigate to be like, yeah, okay, no, that change was actually legit. We do have 200,000 new users, or like that change is legit. We got rid of a bunch of spammers. We have 200,000 less users. Everything, it's okay. Push this to prod.
Is this a conversation around how are we testing our machine learning? How are we testing our big data? Or is this more of a conversation of how do we test a distributed system?
So it's more. It's focused on more sort of how do we test machine learning and how do we test sort of like data pipelines. And to be honest, there's not that much of it which like necessarily applies only to distributed systems. There's just a lot of things in distributed systems that make applying these techniques a little more tricky, right? Like if I was on a single machine, right, like I wouldn't have this problem with this accumulator double counting that I needed to work around. Or like, if I was reading in a bunch of data, I could just actually look at my file sizes and say like, oh yeah, this looks okay, right? But in a distributed system, I need slightly different tooling to help me do the same things that I would want to do as if I was on a single machine. And so it's sort of focused around good practices and how to make these good practices work in a distributed system.
So why did you choose to go with this topic for the talk you're giving at Strata Plus Hadoop?
Yeah. So, I mean, honestly, it's mostly I care about testing a lot, and I get really depressed when other people don't. So it's something that I'm really passionate about, and I want to try and bring it to more people. I do want to try and bring some of the stuff into Spark Core, which is a debate. There's a Jira open for it and the design doc and some discussions. But for now, I have libraries around this for people that are interested in actually testing or doing validation on their stuff today. And I hope that's most people.
So are there some best practices to like a holistic engineering process that includes testing of our Spark programs? What are the changes that people need to make to their engineering practices or perhaps to their engineering organizations?
I think for a lot of things, I mean, don't get me wrong, I love Scala's anonymous functions. Like, they're very easy, but sometimes they can make things a bit difficult to write tests around. And I think sometimes we should look and say, like, yeah, this is actually some pretty complex logic. I want to factor this out to actually make it, properly testable and make some tests around this. There's a lot of sort of like, it works on my laptop, it'll work on the cluster mentality, and sort of, testing by just running it on these really large production data sets, which I don't think is great. I think there's a lot more room to set up proper integration testing environments with like faked out data sources or maybe like small, medium-sized data sources for developers to actually test things. Most of the places I've been don't have particularly good staging or test environments. And I think there's a lot of work sort of, and Docker is making it a lot easier to do a lot of these things. And some people are starting to sort of set up, proper containerized test infrastructures that are easier to do. And I think that's great. But I think we're still very early in those days. And I think we need to be doing more work towards that.
Interesting. What does a properly containerized Spark testing ecosystem on Docker look like?
So I don't have a super great example. Chris Gregory has, because a lot of people don't tend to open source their test infrastructure all that much, because it tends to be like pretty specific to the internals that they're building, right? Like, we have completely different data schemas. My test stuff probably doesn't match yours. Like, I might even have possibly some anonymized customer data in like my test stuff, but like we all know, even putting anonymized customer data on the internet is like terrifying, so don't do that. And so like I might not want to share my test environment with other people. Chris Fregley has some really interesting stuff for containerized Spark, along with a bunch of different other services. And I think that it's actually a really good starting point for sort of figuring out like, oh, these are the services that I depend on, and Spark, of course, as well. And so this is sort of a good starting point, and then you go ahead and customize it to your own needs.
So you're the co-author of a book called Learning Spark. Who is the target audience of Learning Spark?
So the target audience for Learning Spark is really two groups: data engineers and data scientists. And we've done our best to sort of address both of these markets. So there's some parts of the book which are more relevant to data engineers, and some parts that the data scientists care about more. And it's about getting people up to speed with Spark. So if you've already been working on Spark for a long time, Learning Spark is probably a little bit too intro level for you. It's intended for people, the the data engineers. It's intended to help, engineers who are really, really good at being engineers become good distributed systems engineers, right? You might not have a background in MapReduce or, all of the other tools, and it wants to get you up to speed there. And if you're a data scientist, right, you probably have a lot of experience with things like Pandas and sort of doing like single machine analytics. And once again, it's about getting you sort of up to speed in sort of a multi-machine type analytics.
What kinds of challenges do people encounter when they're trying to learn Spark?
So I think some of the earlier challenges that a lot of people I see face is sort of the lazy evaluation trips up a lot of people, especially initially. And then there's also group by key and things like this. So Spark is really, really powerful. And it gives you more than enough rope to hang yourself with. And a lot of times I see people go like, oh yeah, this matches what I want to do. I'm just going to go ahead and do that. And they don't necessarily take the time to read the description of what the function is and sort of understand, oh, this is doing a shuffle. Distinct is actually an expensive operation. Maybe I should do this after I've filtered my data set down a bit later on. And just thinking that way is not something that comes naturally to sort of single machine developers, right? Because, certainly, doing your filter first on a single machine and then distinct could be better, but like it's not going to make a huge performance difference. But in a distributed system, like the ordering of those two operations could be like a very, very large difference.
Yeah. So, and as you've mentioned, learning Spark targets data scientists and engineers. Are there significant differences between what a data scientist should focus on when learning Spark versus what an engineer should focus on?
So I think it depends a lot on your organization. If you're a data scientist, right, you can probably just focus mostly on like the transformations and the actions that you're going to want to be doing on RDDs, and just like you can probably not worry too much about like the super picky details, right? Like that comes down to the person who has to productionize your work later on. But while you're doing your exploratory stuff, right, if it takes an extra 30 seconds, it doesn't really matter, right? You'll grab a cup of coffee. And you probably have a lot more sort of mathematical intuition about your data, and that's great. And you should bring that to your work, because the data engineer later on who's going to be picking this up might not have the same intuition. And they're probably going to be more focused around like, how do I build a robust pipeline? How does Spark actually handle node failure? Is my cluster noisy? Like, what do I need to do if I lose half my nodes? And like those types of problems, which matter more in like sort of long running jobs and less in sort of exploratory work. I think like this comes naturally to a lot of people. We're really good at skipping information we don't care about. So I wouldn't worry about it, right? Like you'll read this book and you'll get to something that's boring and you'll just skip it, even if I tell you to read it. So, I think that's great.
I suppose the lines aren't super cleanly delineated between what is a data scientist and what is an engineer anyway. So,
yeah. I think especially in startups, a lot of people wear both hats.
Yeah.
And in bigger companies, there's maybe more of an exploratory versus production split.
Yeah.
But, as a startup, you probably have money for one and you make them do the job of two.
Yeah. So have you learned anything about how to educate people about distributed systems or big data, whatever words you want to put on it, while you were writing this book? I mean, there's a lot of people like learning to code these days, and they're moving at different paces. Some people move quickly into stuff that is like distributed systems within their like second or third year of programming. So what are the hurdles to educating people about distributed systems when you're teaching?
So actually, yeah, while I was writing the book and even before that and still today, one of the things that I really enjoy doing personally is teaching intro to Spark classes and classes on specific Spark components. Because I find that's when I'm writing a book, I don't necessarily get a lot of real-time feedback about what's confusing and what's not. But when I'm teaching a class, I can see like, oh dear God, no one understood this slide. Everyone turned out. I'll put up another picture of a cat and come back to this later. And so in that, I think the lazy evaluation one, sorry to come back to the same thing so often, doesn't always necessarily stick. A lot of times people will be like, oh yeah, okay, lazy evaluation. I remember that. And then like when it gets to the first exercise and it's failing, they're like, okay, it fails when I do a count, but my count's okay. So I don't understand what's going on. And you have to be like, no, it's cool. Remember, like the count is the action, which is going to trigger your evaluation. So it could be any of the things we were doing before it. So like, let's go back and try and see what happens if we evaluate one of the earlier things. And we'll be like, oh, okay. And this happens more with Python people because the error messages in Python are just so dense and unrelated to what's going on that it can be difficult.
Okay, that makes sense. So I'd like to begin to close off by talking about some of your background with Spark. When did you first get involved in the project?
So my first contribution to Spark was March 24th, 2013. And I don't do a really good job of actually keeping track of like when I've started using technology. So this is sort of the earliest that I know I was using, like actively involved with looking at Spark. And it probably was before then, but I just didn't bother to write it down.
Okay. And like, what was exciting to you about the project when you first got involved?
Sure. So I'd seen Spark before when I had been at Foursquare, but when I really started to get excited the most about Spark, I think I was at Google and I've been using an internal system called Flume Java, which is very interesting. It's sort of also a next generation data flow type language. But being the kind of person I am, internal tools are not nearly as exciting as open tools. And so I was like, this is really cool. I wonder what's open source that can give me some of the same power. And I found Spark and I was really excited because I'm a functional programming nerd and it was written in Scala and I love Scala. And I was like, oh my God, this project is the best. We should be friends. So that's sort of like how I got really excited about Spark and went from there.
Okay, interesting. So you know, at this point, you've been working with Spark for a while. You've worked with it at a variety of places. How does the perception of the Spark ecosystem and the usage of Spark, how does it vary across the tech world?
Yeah, there's some people who certainly think that it's a magical pixie dust and it'll fix all of our problems. And those people will probably be disappointed once they write software using it. But most people are actually, I think, coming from a like, I want something that's faster than MapReduce, and I want something with like a maybe more consistent sort of ecosystem. I'm tired of maintaining all of these separate tools, and I want something that sort of comes together. And I think they're really excited about that. And I think there's some people who, when I talk to them, they haven't even really noticed that there are these different components in Spark, right? They're used to working with the components that they use today, but they've sort of forgotten that there's all of these other components available for them once their data needs these types of transformations.
Cool. Well, I think that's a great place to stop. I mean, was there anything else you wanted to mention about your work, or where you think Spark is going, or any last parting words you'd like to give?
I mean, yeah, I'm really excited about Spark 2.0. It's still in the very early stages, but it's very exciting to see sort of the wonderful growth of the community. It's gone from a very small number of people, mostly focused around Berkeley and the App Lab, to this very large project encompassing so many companies. It's really wonderful to see the growth of the project.
Awesome. Well, Holden Karau, thank you for coming on to Software Engineering Daily. It's been really great talking to you.
Awesome. Yeah, thanks for having me.